Hi, students and friends. This is your host and teacher Sayyid Ayazuddin. You're watching Learn and Teach by Sir Ayaz. I'm continuing my O-level past papers session, and this time I have selected IGCSE Chemistry 0620. Now, I have October-November 2024 session, and the variant is 61. I'm not going to talk about the other details. You all know it's paper 6 alternative to practical. It's 1 hour. You have to answer all the questions in the question paper. You can use calculator. The total mark for this paper is 40. Important thing, notes for use in qualitative analysis are provided in the question paper. It's like this. This includes tests for anions, tests for cations, tests for gases, as well as tests for flame. Flame test for the metal ions. So let's start the paper. Here's question number 1. A student has a mixture of copper 2 carbonate powder and crystals of sodium sulfate, copper 2 crystals of sodium sulfate. Copper 2 carbonate is insoluble in water. Sodium sulfate is soluble in water. The student tries to obtain pure copper 2 carbonate and crystals of pure sodium sulfate from the mixture. Figure 1.1 shows four of the steps the student carries out. So in step 1, student has added distilled water to the mixture and stir means mix. Step 2, filter the mixture. Step 3, heat the filtrate from step 2 until crystals start to form. Step 4, leave the residue on the filter paper from step 2 in a warm place to dry. A. State what happens to the sodium sulfate in step 1. If you look at the information, they have already explained that sodium sulfate is soluble in water. So what you will write? You will write dissolves. It will definitely dissolve in this water. So what is removed from the filtrate in step 3? So here's step 3. You're heating the filtrate, which is obtained from step 2. It's definitely water. You heat the solution, you will remove the water. So I will write water. C. Describe what must be done after the filtrate has been heated in step 3 to obtain a larger amount of sodium sulfate crystals. Definitely, you have to leave it to cool down. So I will write leave it to cool. Into next part D. 1. State what must be done to the residue before it's allowed to dry in step 4 to obtain pure copper 2 carbonate. Definitely, copper 2 carbonate, as you know, you can see here, it's insoluble and you are obtaining this as residue here. It has to be washed with distilled water in order to remove the soluble sodium sulfate. So I will write wash with distilled water. Part 2. Identify the substance removed from the copper 2 carbonate in D1. Sodium sulfate is soluble in water. So it must be the one which is present in the residue. So you write sodium sulfate. Next question, which is question number 2. A student investigates the reaction between aqueous magnesium sulfate and aqueous barium nitrate. A precipitate of barium sulfate forms in the reaction. The student does 8 experiments. Experiment 1. Fill a burette with aqueous magnesium sulfate. Run some of the aqueous magnesium sulfate out of the burette so that the level of the aqueous magnesium sulfate is on the burette scale. Fill a second burette with aqueous barium nitrate. Run some of the aqueous barium nitrate out of the burette so that the level of the aqueous barium nitrate is on the burette scale. Add 4 centimeter cube of aqueous magnesium sulfate from the first burette into a 10 centimeter cube measuring cylinder. Add 1 centimeter cube of aqueous barium nitrate from the second burette into the same measuring cylinder. Place a stopper in the top of the measuring cylinder and invert the measuring cylinder several times. Leave the measuring cylinder to stand for 15 minutes. Record the level of the precipitate on the measuring cylinder scale. Rinse the measuring cylinder with distilled water. Experiment 2. Repeat experiment 1 using 1.5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. Now they have changed the volume of barium nitrate used here. Experiment 3. Repeat experiment 1 using 2.5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. Experiment 4. Repeat experiment 1 using 3 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. Experiment 5. Repeat experiment 1 using 3.5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. This time they used 3.5 centimeter cube. Experiment 6. Repeat experiment 1 using 4.5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. Experiment 7. Repeat experiment 1 using 5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. Experiment 8. Repeat experiment 1 using 5.5 centimeter cube of aqueous barium nitrate instead of 1 centimeter cube. A. Use the information in the description of the experiments and the measuring cylinder diagrams to complete table 2.1. So volume of aqueous magnesium sulfate in centimeter cube, it's same in all the experiments. So you will write 4. What about volume of aqueous barium nitrate? So it's 1 in the first experiment, but in the second, from second experiment till 8, they've continuously changed the volume of barium nitrate. So in experiment 2, they have added 1.5. In experiment 3, 2.5. In experiment 4, it's 3. In 5, it's 3.5. In 6, it's 4.5. In 7, it's 5. And in 8, it's 5.5. Now here we are having measuring cylinder diagram showing solution with precipitate. Now you have to write down the level of precipitate on the measuring cylinder scale in centimeter cube. For instance, in the first one they have shown it's 1.2. So what about the second experiment? It is 1.1234567 So I will write 1.8 here. So in experiment 3, it's 3. Experiment 4, it's 3.123456, 3.6. Experiment 5, it's 4.12, 4.2. Experiment 6, it's 4.123456, 4.6. Experiment 7, it's same as well as in experiment 8. Part B. Complete a suitable scale on the y-axis and plot the results from experiments 1 to 8 on figure 2.1. Draw 2 straight lines of best fit through your points. The first straight line should be for the first 5 experiments and must be extended to pass through 0, 0. The second straight line should be for the last 3 experiments and must be horizontal. Extend the straight lines so that they cross each other. So for your convenience, I've already drawn the graph, and the graph you'll be obtaining, it's like that. The line for the volume between volume of BnO3 between 4.5 till 5.5 is not straight, but I think it's okay. For the other points, I've drawn it a straight line. I've joined it correctly. You will get the graph like this. So let's move to part C. Use figure 2.1 to reduce the level of precipitate on the measuring cylinder scale when the experiment is repeated using 2.8 centimeter cube of aqueous barium nitrate. 2.8 centimeter cube of aqueous barium nitrate. Show clearly on figure 2.1 how you worked out your answer. So 2.8 centimeter cube of aqueous barium nitrate. 2.8 must be here. This is 2.8. Right, 2.8. Now they are asking level of precipitate. Let's join the level of precipitate. It must be 3.123, 3.3, 3.3 centimeter cube. 3.3 centimeter cube, according to our work. Part D. The student repeats the experiment using 6.5 centimeter cube of aqueous barium nitrate. Predict the level of precipitate on the measuring cylinder scale. Explain your answer. You see, after 4.5, there won't be any precipitate obtained. The last level of precipitate on the measuring cylinder is, according to this, 4.6 centimeter cube. So it will definitely remain as it is. So prediction. So we'll write 4.6 centimeter cube. And for the explanation, what you're going to write, you have to write so that all the magnesium sulfate has reacted. We don't have any more magnesium sulfate that will react. So we'll write all magnesium sulfate has reacted. E. Sketch on figure 2.1 the graph obtained if all of the experiments are repeated using aqueous barium nitrate of half the concentration used in experiment 1 to 8. So now this time you are using half the concentration of this volume. So if you will see this 4.6, 4.6 is the final volume, final level of the precipitate. So you must be getting like 2.3. It must be 2.3. Graph must be leveling off at 2.3. It must be like that, 1, 2, 3. At this point, 2.3. And for the volumes, so I'm using the half the volume. Using purple here. Three. So half the volume means the first reading 1. So it must be 0.5. For 0.5, 0.5. So the second one, so 1.5 must be 0.75. Third one, 2.5. So it must be 1.25 somewhere here, like that. Then we are having 3, 1.5. For 3.5, we will be getting 1.75. Yes, it must be 1.75. For 4.6, we're getting 2.3. So this will be the final graph you'll get in this case. F. Suggest why the measuring cylinder is inverted several times after the aqueous barium nitrate is added. So the reason is that in order to mix the reactants or solution, so there will be uniform or equal distribution of concentration throughout the mixture. In order to mix the reactants, so that there will be equal distribution of concentration. Throughout the mixture. Suggest why the measuring cylinder is left to stand before the level of the precipitate is recorded. The reason is that it's left to stand so that will allow the precipitates to settle down. Precipitate will settle down. Moving to next part, which is part G, part H. The volumes of both aqueous solutions are measured using burettes. 1. Give a reason why burettes are used rather than measuring cylinders. Definitely burettes have higher level of accuracy. So you write burettes have higher accuracy than measuring cylinder. Part 2. Suggest why burettes are used rather than volumetric flasks. Volumetric pipettes. Volumetric pipettes are used for fixed volumes. So we don't need fixed volume in each experiment. So you write fixed volumes are not used in each experiment. You have to mention because we are carrying out more than one experiment and we are not using fixed volumes. We have variable volume. Moving to the next question, which is question number 3. A student tests two solids, solid T and solid U. Test on solid T. Solid T is lithium sulfide. So they gave us the name of the compound, which is lithium sulfide. So it must be containing Li plus and SO3 2 minus ions. Complete the expected observations. A. The student carries out a flame test on solid T. Observations. Definitely, this observation will be due to the presence of this Li plus ion. If you look at the flame test here, here's flame test for metal ions. Lithium, it gives red color, so I will write red here. Student dissolves the remaining solid T in water to form solution T. The student divides solution T into two portions. B. The student adds the first portion of solution T to a test tube containing acidified aqueous potassium magnate 7. State the color change. So it's containing sulfide ion. It must be the test for sulfide ion. If you look at the list of anions here, there's a test for anions. So we have sulfide ion here. If you'll add small volume of acidified aqueous potassium magnate 7, the result will be color changes from purple to colorless. So we write purple to colorless. C1. To the second portion of solution T, the student adds excess dilute nitric acid. The gas produced turns filter paper soaked in acidified aqueous potassium magnate 7 white. Identify the gas produced. So is a test for the gas produced here. So the test for the gases. It must be sulfur dioxide gas. Returns acidified aqueous potassium magnate 7 from purple to colorless. So the gas produced, it must be sulfur dioxide. So I will write sulfur dioxide. Part 2. To the solution produced in C1, the student adds aqueous barium nitrate. Observations. So we are having only Li plus and SO3 2 minus, and this test, barium nitrate, is for the presence of sulfate ion. If you look at this anion, sulfate ion will be tested with aqueous dilute nitric acid and barium nitrate. So there won't be any change there. So I will write no change. Test on solid U. Solid U contains one cation and one anion. So they are talking about solid U. It's containing only one cation and one anion. Table 3.1 shows the test and the student's observations for solid U. The student dissolves solid U in distilled water to form solution U. The student then divides solution U into three portions. Test 1. To the first portion of solution, you add a few drops of aqueous ammonia. Observations. Green precipitate. It must be the test for the cations. If you look at the test for the cations, the test is with aqueous sodium hydroxide and with aqueous ammonia. And they are saying green precipitate. So green precipitate means it can either have chromium 3 plus or Fe2 plus. Both will give green precipitates. Test 2. I'll write here Fe plus 2 or Cr plus 3. To the second portion of solution, you add 1 centimeter cube of dilute nitric acid, followed by a few drops of aqueous silver nitrate, yellow precipitate. It must be the test for halide ion, that is chloride, bromide, iodide. The test. You see, you have to acidify with dilute nitric acid, then add aqueous silver nitrate, and they are saying green precipitate. Green precipitate means it must be having, sorry, they are saying yellow precipitate. So it must be having I minus. Test it to the third portion of solution. You add 1 centimeter cube of aqueous chlorine. The solution turns brown. Now, it must be the salt of iodide. Salt of iodide or iodide salt. Because chlorine is in group 7, it's above iodine. In group 7, we have fluorine, bromine, iodine. Chlorine's above iodine. It's more reactive. So it will definitely displace these two. So you'll get the iodine as a result of this here in this case. And due to the formation of iodine in the solution, it will turn to brown. Formation of I2. B. Identify two cations that the test and observations in table 3.1 show could be in solid Q. So it must be, as I have already mentioned, Fe plus 2 or Cr plus 3. The reason is that they didn't give any further information about what happened to the green precipitate, whether it's soluble or insoluble in aqueous ammonia. So I will write iron 2 and chromium 3. So these are the two cations that might be present. E. Describe an additional test that the student could do to confirm which one of the two cations identified in D is in solid U. Give the expected result for one of the cations. So you have the test for the cations. It's either with aqueous sodium hydroxide or aqueous ammonia. So in case of aqueous sodium hydroxide, chromium 3 plus ion, green precipitate soluble in excess, but not with Fe2 plus. It's insoluble in excess. But in case of aqueous ammonia, both of these are insoluble. So I will go for aqueous sodium hydroxide. The test must be add excess sodium hydroxide. As you are having solutions, so no need to write aqueous here. Water is already there. If you want, you can write aqueous here. Now for the cations, you have to mention one of these, that is chromium. Three ions form green precipitate that dissolves in excess. Or if you want, you can even write for Fe2 plus, that is iron 2 forms green precipitate that is insoluble. Remember, you have to write the result here. Result that what will happen, whether it's soluble or not soluble, dissolves or not dissolves. Here in this part, you can write either of these, either for chromium 3 or iron 2. F, identify the anion in solid U. Definitely, I've already identified it's iodide. So you write iodide or I minus or iodide. Moving to the last question, which is question number 4. Beetroot is a colored vegetable. The color is caused by a mixture of water-soluble colored compounds. Plan an experiment to find how many water-soluble colored compounds that are in a beetroot. Now they are saying you have to find how many colored compounds there are in beetroot. They are talking about the number of colored compounds. Include in your plan how to extract the colored compounds from a beetroot, how to separate the mixture of colored compounds, how the results show how many colored compounds there are in a beetroot. You are provided with a beetroot, distilled water, and common laboratory apparatus. By looking at the question, it's definitely clear that you have to go for the method of chromatography. So it must be chromatography. So first of all, we need to crush or grind this beetroot. Crush or grind beetroot. The next step, name the apparatus used in this case using mortar and pestle. Dissolve this in water. Now the solvent uses water. You will write solvent used is water. Now mention the name of the technique. You can either write use chromatography or chromatography paper. Or chromatography paper. Now place the color on chromatography paper. Place the color on chromatography paper. Dip the paper in water. Dip the paper in water. Water is a solvent. We have to dip it in water. Now, different colors, they give different spots on different locations. So it means that number of colored substances is equal to number of spots. Number of colored substances is equal to number of spots. So in this way, you are going to gain full 6 marks for this question. Thanks for watching. Press like and share my videos. For more videos, subscribe to my channel and press the bell icon.